All right, let's get back into it. We are doing digital circuits, and we're gonna have some fun. Probably. Last time on digital circuits, last time we talked about K-maps. We talked about don't cares. We also talked about logic gates and other stuff, but mostly we're going to talk about K-maps and don't cares because we're going to do some more fun with it. Okay, so K-maps. I might have not explained it in the last one, so I will double explain it here in case if we did have it in the last one. Let's say you have a K-map, right? You have x1, x2, you have 0. Oh my gosh. 0, 1, 0, 1. And you have inputs in here that they're in the form x1, x2. So you have 0, 0, 0, 1, 1, 0, 1, 1. And so, this is basically one thing to realize about K-maps is that the coordinates, like the sides here, represent like coordinates. So this is like 0, 1, 2, 3. And then we have, let's say, x1, x2. This is going to be 4 variable one. I'm not going to go into all the binary conversion here, but if you want to, you can also do that. So if you do your standard gray code, so 0, 0, 0, 1, 1, 1, 1, 0, and then you do the same thing over here, 0, 0, 0, 1, 1, 1, 1, 0. And then if you were to like put x1, x2, x3, x4 like into like these specific coordinate ones, you'd have first you have 0, then 1, then 2, then 3, then 4, then 5, and then 6, then 7, and then 8, 9, 10, 11, and then you have 12, 13, 14, 15. You can get these from just putting x1, x2, and x3, x4, and then convert this into decimal. So choose. And as with the other K maps from before, if you same idea. If you want to if you want to get product of sums, or sorry, products, which one is it? But if you want to like get a cover for it, then that will be your way on how you can derive a function from the truth table or K-map if you already provided a K-map. That being said, it is possible for us to have something known as multiple. Okay. Oh, okay. Multiple. Did it erase? Yeah, it erased everything. Okay, hold on. It's also possible for us to have something called multiple output functions. And basically these are like, let's say you have these are like see, let's say you were to optimize a K-map for one function only, and then for another function individually, the cost of implementing both of them separately is often greater than what it would take to just implement them simultaneously. So let's say you have, I don't know, you have an AND gate, right? And say this one end of this AND gate goes here. You have this AND gate. You have another AND gate as well. Right. And ooh, no, we'll do an OR gate. All right. And let's say this is F and this is a G. You have x1, x2, x3. The simplest way you could have F, ignoring like pretend like you don't have G here, is it just to have F is equal to x1 and ANDed to x2. And for G, it'd be same, very similar. It'd be x2 or oops, or x3. Now you can actually you could optimize this probably a bit better than what I have over here, but the point is that F and G both rely on x2 over here. So if you had a more complicated circuit, and let's say x2 and x1, um, let's say like G also dependent on x1 in some way, like let's say you have another AND gate. Instead, now it's going to be x2, x3 ANDed with x1 and x2. Right there, you could possibly find this would be like at the end of a result of optimizing. This would be a way to have both your functions, optimized, but at the same time, so you don't have to, add redundant AND gates, and also make sure to hydrate. So with those, you can do like with K maps. You would find, let's say, like you have a K map, right? You have some min terms that you go over, right? Some min terms that you go over here, right? And you have another min term over here. And then let's say that like this is for a function h, and then you have another function, let's call it k. And it's very similar to h, except it kind of looks like this, right? You'll notice that you have a common group here, but you have an uncommon group here. You could implement both h and k at that first step with these two groups, and then for h and k, like their individual, like their differences, you just have to add another AND gate, or just add a change to an OR gate, or whatever you need, and that'll be more than enough. Actually, sorry, not more than enough. It'll be most optimized for both of those functions without having to, create one for h, create one for k. With that, we will go on to multi-level synthesis. So this is more important when you get to like buses and parallel inputs, where you have like a bunch of inputs going into like a single logic gate, and you want to know, oh, is any one of them on? Are all of them on? Or is only one on? Right? You could use AND or XOR. But like as you try to increase the amount of inputs, that increases the fan in. So if you increase the inputs, so number of inputs, I should say, number of inputs, you also increase the fan in. And this kind of fan in gets to be a big problem, because at some point in the real world, you're going to have, it's going to be more costly to develop chips that support more features, like let's say, think of like a classic example. I have the KF74 HC integrated circuits, and trying to put like 8 inputs into something is nearly impossible. I only have like 2, 3, maybe 4. There's also some 6 input ones, but as you get to more and more inputs, it gets costlier and costlier to make those inputs. So when you are making stuff with a huge amount of inputs, what you'd rather do, instead of having like one like big like AND gate and doing that, what you might want to opt to do is to like split the inputs up, make a 4 input, and then you take another 4 input, right? And then you could take like a 2 input here. Actually, how much do I have? Yeah, it's 9 input, but you'd have, hold on, I'll make this a little bit more accurate. You have a 3 input, you have 4 input, it's a 9 input, okay. There we go. You have a 4 input, you have a 2 input, you have a 3 input, and then those go into a, oh, wow, okay, Excalibur. It goes into a 3 input AND gate, and here, like this one is maybe a bit more expensive, but this one is really cheap. This one is relatively cheap, and this one is also relatively cheap. Right, as compared to this, where it's like, hey, does anybody know where a 9 input AND gate is? it's just not. It's just not common, and it's costly, and too many problems come from it. Uh, there are two methods for doing this. One method is something called it's factoring. So taking a look at your expression, seeing if you can simplify it. And another one is function decomposition, which is actually a little bit more like specific. Um, Basically, what you try to do, like I kind of give an example circuit. Oh wait, that's not really great. It's not very convenient. Where you try to make a function within your circuit. So let's say you have AND gate. Actually, I'll just copy this example from my notes. Yeah, okay, so this bad boy is an inverting buffer. And you have another one. This one goes into another inverting buffer, and that just feeds into there. And then you OR it. Then you get G over here, which is an inner function. And then G, you then invert it, feed it into an AND gate. This is X4. I'll just put these here. More often than not, you're going to be doing factoring, because function decomposition is, let's say, it's like almost like kind of like a scenario that is kind of too perfect to have, right? It doesn't really always work in like that in the real world, but like it's something that can be done. But then you have your final function output here, and it was originally, if you want, I can actually just write out the original function out here if you are curious on how on the original thing. I can okay. I'm humming and hawing about it. I actually don't think I'm gonna go through the entire derivation. But I will just write out the original function here. It's a sum of products, which is my favorite. I love sum of products, and I'm not even being sarcastic about that. Like it's actually one of the like nicer kind of things. I'm not really too big a fan on what we'll call it max terms, product of sums. I mean, it's okay, but like I don't like it. Oh, my mic is not picking this up, but I don't really like it. Okay, maybe I repeated it, but oh well. Yeah, here's the function, and if you want to go along and try to factor this out into this one over here, you're more than welcome to. Actually, I'll give you a hint. G x1 2 is equal to x1 inverse x2 and x2 inverse x1. And there you have it. Okay. Now, let's move on. I want to kind of move on because there is so much content in digital circuits. It's actually kind of crazy. So now we'll talk about this is kind of a build up to something called the tabular method. So literal, okay, is basically each appearance of a variable. So each appearance of a video, not video, variable. So let's say if you have x1, x2, x3, this is something called a 3L implicant. And what is an implicant, you ask? That's a good question because I'm going to be talking about it right now. The implicant is if a function, so okay, so basically, if you have a product term, right, a product term that take basically equals 1. Okay, so okay, it's so if a product term equals 1, and then the function equals 1, then that product is an implicant. So basically, this is just a fancy word of saying minterm. So if you have something that's guaranteed to give if you have something that contributes to the function being 1, it is an implicant. Which is basically any minterm. It's basically just minterms all over again. Then you have something called a prime implicant, which takes on a value of 1 when no other when no not no other that I'm thinking about exclusive essential prime implicant that I'm thinking of. Prime implicant is an implicant that does not contain another another implicant. So if you have, let's say, x1, x2, x3, x4, and you had another one that contains x1, x2, x3, that for one, it contains another implicant, right? So x1, I'm going to make it a little bit sophisticated, x3, x4, complement. You have x1, x2 complement. This is not a prime implicant because it contains whatever you have here. Simple dimple. Cost is, well, same as usual. Number of gates. Gonna do shorthand here. Number of gates, and it's going to be number of inputs plus number of inputs. I notice that complement inputs are free. The reason why we say that they are free is because yes, you can you could add a not gate at the very beginning, but it wouldn't really give add to the complexity or cost. You could derive that outside of the digital circuit. Um, so you don't really need to consider them for cost. But if you have a complement gate, I should say not gate. If you have a not gate included in the implementation, then it is part of the cost. So complement, how should I put it? Complement intermediaries or intermediates are included in cost. Okay, that's basically it. And then we go on to the big daddy tabular method. Give me one sec. Okay, so I'm going to talk about tabular method. I'm actually going to type it out. Otherwise, you're going to see me writing for a while and getting very tired. So, tabular method is useful when we have more than five inputs. This is because for K-maps can only handle less than or equal to 5. So you can, I don't know why you'd have a one variable K-map, but for like two variables up to 5 variables, that's where K-maps really tend to shine. However, more than that, and then you'd have to think about stuff in 40, which is going to be hard. So this is useful for that scenario. It's basically taking K-maps, but uh, getting rid of the graphical part of it and going and making it, more like tabular based, table based. So, how do we do this? So, first you're going to minimize the prime implicants. And then, so minimize implicants in general. No, prime implicants. And then you're going to okay. Uh, hmm. I misread it. So tabular method seeks to find the most minimal implementation possible. There are like for K-map method, you have multiple ways of having the same thing. But for tabular, if I remember correctly, it is going to give you the most efficient, like most cost optimized, cheapest implementation possible. So the steps for a tabular method is to generate prime implicants. So you're going to find implicants that don't contain other implicants. Then your second thing is going to be finding essential prime implicants. So this is where you get rid of some prime implicants that don't matter. I should probably talk about what essential prime implicants are. Okay. So now I will do that really quickly. I will also talk about cover. So cover is basically a collection of prime implicants well, not prime implicants, just regular implicants that basically cover all possible all possible out it cover all possible inputs that give the function an output of 1. Right. So prime, yeah, okay, so something to note is that a set of prime implicants that make up, if you have like a cover that's only made up of prime implicants, then you have the cheapest solution. And then you have something called essential prime implicants, I'll just call it PI. And this is basically prime implicants that cover an input that no other implicants cover. So let's say, to give an example, I will draw a K-map. When we were doing K-maps, we did like these groups, right? These are now our implicants. Okay, so let's say you have, okay, let's say you have this guy. This guy's a prime implicant. This guy is a prime implicant. This guy's also a prime implicant as well, because they don't contain other implicants. This one that's covering over here is also a prime implicant. However, these ones are essential because they cover ones that no other implicant covers. So like these three are not covered by anything else. These two are not covered by anything else, and these three also are not covered by anything else. So when we're talking about finding these essential prime implicants, that's what I mean. That's we're trying to find the implicants that cover inputs that no other implicant covers. So continuing in that vein, if our cover well basically covers all possible valuations or inputs, then we are done. If not, then we continue until we are done. So, yeah. So how to do this? Should I write up? Okay. So basically, this I'm gonna kind of make it into here. So to generate these prime implicants, what we're going to do is we're going to put all implicants into a list. And this is called list 1. In list 1, what we try to do is we organize the implicants based on how many variables give one number of, yeah, okay, based on number of ones in the binary representation of the implicant number. I think it'd be easier to show what I mean here. And then when you what you do then is then you take a look between, let's say, the group contain, let's say we're where the binary representation contains 3 ones. So let's say we have one with 3 ones over here, and we have another one with 2 ones. What you're going to do is you're going to take a look at the group of 3 ones that is only one change away from the group of 2s. Again, I will go over an example of this in just a little bit if you are kind of confused for now. Otherwise, I'll continue. Then you will take a look at the ones which have the in common between 2 and 3. So like everything else is the same except for, let's say, I'll kind of give an example. So let's say you have 1100, right? And you have 1001, and you have 1010, and this is all in group 2, right? You have 2 ones, 2 ones, 2 ones in here. And then your next group, you have 0101, you have 1011, and you have 1101. So between 0111 and 1001, you can't change just one of these bits to get to 7, to 0111 here. If you're really curious, I'll just put what it's 12. The thing that's scary about digital circuits is how fast you learn binary representation of numbers. So So between 9 here and 7 here, there isn't a common bit, right? I'd have to flip 3 bits here in order to get 7 here, which fails a requirement. We need to have only 1 bit changing. Between 1 0 between 0 and 1 and here, same deal. You'd have to change 3 bits, or yeah, again 3 bits. For 11 here, you between 9 you have to change 2 bits. You have to change 0 1 to 1 0. Between 11 and 10, that we're actually doing good over here, so I'll put a check mark. I can't really put a check mark, but same special meaning. And you'll kind of I'll call check one here, because they are now grouped together. Now between let's say 1010, so between, if we do the same thing with 11 and 12 here, we'd actually have to flip 3 bits, so we can't go along with what we have here. For 13, again, doesn't work with 9, doesn't work with 10, but works with 11. Oh, with 12. So we're going to call this check 2. Check 2. So this is list 1. Now, what you do is you create a new list with the ones that you checked marked, the ones that you've paired up. So and keep in mind, this is the 3. I should probably put in like a kind of thing here. This here is the 4L implicant. Put a pipe character, and then you have min-term number. Yeah, here. So 9 here is min-term number 9, min-term number 10, and min-term. You get the idea. So then now you create a new list. This one's called list 2. Very creative, by the way. And then you will say, okay, which min-term numbers are you combining? I can't really do that. Okay. Min-term numbers. And then you'll have the 3L implicant. And then we go from there. So now that we've combined 10 and 11, we're going to put 10 and 11 here. And now we have, well, what is the only bit that changes? It's the last bit over here. So you're going to have 101x. Okay? And then you would go between 12 and 13s, 12 and 13, and you'd go, okay, so this is going to be, well, the only bit that's changing is the last one over here again, so you could do 110x. Now, suppose if you had another one, actually, I will probably. Yard. 110. Okay, what I will do is I'll make a new one. This is going to be 14. And then this is going to be a new group, and this is going to be 15. Just to show that you can actually go further with this. These two are same thing over here. And then in the new list, do 14, 15. Oh, I keep on pressing random keys and it does random things. Who knew that would do that? Then you have 111x. What you notice is that between, well, okay, this one doesn't match up with anything, but 12 and 13 and 14 and 15 can actually be combined again. So what you will do here is you'll keep on going until you can't combine anymore. So we have 13, 14, 15, 12, 13, 14, 15, and that will now become 1xx, right? Because 0 and 1 in the third position is the only bit that's changing between these two. Now this one is quite equivalent to what you'd see in your K map. over here, so 12, 13, 14, 15. It would be like going like around this one, like that, as in a regular K map. Tabular method is all about just K maps, but without having to use graphical representation. So yeah, you'd continue on that path with making new lists until you're done. Until you can't generate more, can't match up more stuff. Then you will take a look and see, okay, I have some, I will call this one P1, and you take a look at what you have in check mark. So check 1, check 2, well, check 1, 2, and then this will become okay, I'll call this one P1, 2, call this one P4, and we'll call this one P5. So now you have some minterms here. And let's go about how we would actually eliminate them or finding the essential prime implicants. Because what we have here now is a bunch of implicants that kind of just have everything. So I will make a table. And I'm going to call it prime. And you have 0. This is the min terms, by the way. 0, 2, 3, 4, 5, 6, 7, and it will have. We have 15 minterms. Actually, no. Sorry, we don't need to list everything because we just need to list the ones that we have here. So P4 has 12, 13, 14, 15. P5 has 10 and 11. P1 has 9. P2 has 7. So we actually just need to start from 7. So M7, M9, M10, 11, 12. M13, M14, M15, M16. So, and yeah. So we have P1 here, which is going to be 1, 0, 0, 1, and it's going to be only has midterm 9 over here. P2, which is 0, 1, 1, which is going to be there. P3, which is 1, 0, 1x, which is going to have M10, M11, P4, 1, 1x, and this one contains, it's no midterm 16. And okay, so I kind of screwed up a little bit because I'm not saying anything wrong. The thing is, I want to kind of show two more concepts. Actually, we can kind of pretend here. So this is what we actually have. But let's say, well, let's just get rid of these, and so let's say we have more, like, let's say we have some that overlap, right? When you're doing this checking over here, you check all the possibilities. Actually, you also have 1, 1x0 here as well. If I'm not mistaken, 1, 1x0. Yeah. So no, you do. You have 1, 1x0, which is going to be 12 and 15. 1, 1x0. And you also have another one, which is 10 and 14. Oh no. It's going to be 1x10. Yeah, 1x10. And actually, we actually need to make up stuff here. Okay, I don't know. I tried to desync control Y, it didn't work. So then we have another one. We can actually just what I will pretend to do. Okay, so then we'll call this one. Goodness. That was P3, now it's P4, and then we'll call these ones P5, and we'll call this one P6. So P5 is going to be, which one? Let me just check. P5 is 1x0, and P6 is going to be 1x10. Right, okay, and then P5 covers 12 and 14. So since we 12 and 14, and this one it covers 10 and 14. Okay. So now let's talk about row domination and column domination. Poor Wasef, when he mentioned this in the classroom, so much giggling happened. Okay. So what happens? Okay, so our first matter is to actually we're going to first, okay, yeah, before we discuss row domination, column domination, what I will do here is I'm going to take a look at what's the essential prime implicant. Are there any implicants here that cover min terms that are not covered by anything else? Yes, we do. So I will get rid of P2 over here and P1 because M7 and M9 aren't covered by anything else. So if you have, let's say, any min term here that's not covered by anything else, you delete it. You get rid of it. Additionally, and P3 over here, P3 covers an essential one. Okay. So P3 is also there because we get rid of here. Okay, so then that leaves us with, oh, but you can make this table again to make it even cleaner, but you don't have to. If you prefer to work with just one, which I kind of do, you can just leave it as is. So let's talk about row domination and column domination. So row domination is when, let's say, okay, we have, let's take a look. So P4 here covers M12 and M14, right? P5 also covers M12 and M14. However, notice that P4 here covers also 13 and 15. Because P4 covers more than P5 in the row, we can this is something called a row domination. And right now, P4 row dominates P5. So then this means that you can remove P5. Right, and then you have P4 and P6 here. Now, in this case, you couldn't eliminate anything else because P6 covers, actually, no. Actually, no, you, actually, yeah. So take a look. P3 also gets rid of, covers M10, and P6 also gets row dominated by P4. There is another case that I'm thinking about. which is column domination. So it's kind of so with column domination, how you do it is take a look at P4, P5, P6. If you notice for midterm 14, you have these three over here. And for N12, you have these two, which is covered by P4 and P5. And what you can do in column domination is to remove the dominating, because then you have something that is already covered by the take a look. So P4 and P5, it's kind of closer to an essential prime implicant because it has fewer implicants covering that minterm. But with with M14, with P4, 5, and P4, P5, and P6, you have that they are actually like they're all covering the same thing. It's less of a prime implicant, if that makes sense, right? There is more prime implicants covering that one midterm, which makes it a less more redundant, if that makes sense. So when you take a look at this column domination, you want to take a look at the prime implicants that cover. Hold on. Hold on. Want to make sure I get this correct. 1 second. And there, I'm still correct. What you do when you have this column domination here is you delete this column like this column that dominates the other, because it's more redundant. You can kind of just toss it aside, and it will be covered. Actually, but it will still be covered by P4 and P5. I don't think there's an instance where or deleting column here would actually lead you to losing an input or losing like something from Python. Okay. Otherwise, so you would see that M14 column dominates M12. So then you're going to remove 14. Okay. And that's basically it for tabular method. What you do is then you take a look at, well, what are my surviving midterms? What's survived the purge? And you can see that we have P2 is guaranteed, P3 is guaranteed. You need it. Sorry, P1, P2, P3, and P5. P5 here actually is not essential since it's already covered by P4, but you could take P4 here since P3 and P4 all cover everything over here. So you don't need either P5 or P6. Okay? That's what I mean. Like when you're trying to take a look at the cover, you're trying to take at what has the least overlap. Like if I had another prime applicant, let's say P7, right, and it covered between P11, M11 and M12, right, P7 would choosing a cover of P3, P7, P4 is kind of useless because you can get a simpler cover, a more efficient cover with just P3 and P4 over here. Right? P1 and P2 we can't get rid of for obvious reasons. So that would result with our final cover being P1, P2, P3, and P4. And these ones are, take a look at what we have here. 1001, 10111. And then you have 101x and 101xx. So 101x and x. Now, something need to consider is that these guys, like when the more x's they have, the cheaper it is. So remember from last week, I kind of went over. I'll actually just pull it up right now. If we take a look here, I said, okay, well, this is zoomed down to the bottom. So this purple one over here, this square one, actually requires less logic gates to implement than one of these small two ones over here, right? For this one over here, you'd have to have x3, x2, x3, and x4. But for this one, you could just have, you just have to have x3, x3 and x4 prime, right? You just need to use x3, x4 prime, and just to represent this four group. And in the similar vein, that's what happens here. This one with two x's is actually cheaper than this one with one x, and this one is actually cheaper than both of these. So there are some instances where you want to consider this, where you'd rather have let's where you'd rather have that. So if you can pick a cover that has more X's in it, then go for it because that will be the cheapest cost physically. Uh, it may not be the like it may not be like the like a very efficient cover here, but it would mean that your cost in real life would actually be smaller. So P1, P2 is going to be midterm 9, midterm 7. And these ones have their own midterms. Midterm 11, 10. And this is going to be M12, M13, 15. And you could just do, okay, x1, x2 plus x1, x2 prime, x3. And this one you do x1, x2, x3 prime, x4. And this one you do x1 prime, x2, x3, x4. Sum them all up, and then you can actually factor them more efficiently. I'm not going to go through it right now because they're more important things to talk about, but that would be how you would get that's how you would get, let's say, the cheapest implementation. And this would be the cheapest implementation that you could make of this function. And this would be this would come from something like you have a function is equal to 9, 10, 11, 12, 13, 14, 15, right? That's how you'd see it in an exam question, in a test question, and that's how it would go. So now, that is, I guess, okay. I didn't really take good notes on it. Off we go to kind of improvise. So, now that we've sort of covered what you would need for generating the lowest cost implementation, let's go on and consider different, like more higher level elements. So right now we've talking about and, talking about or, talking about not, and all the other gates. We're going to go into something a little bit higher level, and that's called something called a multiplexer. Okay, so a multiplexer, it has a specific shape, but I'm going to start off with the circuit diagram. So we have a select, and we have an AND gate, W1, we have W2, right? And And hold on. It's supposed to be one output. Give me a second. And I found out, yep, I was thinking it was right. I was just not confident in it enough. And this is a multiplexer. So what does a multiplexer do? Basically, it's as if, okay, think of it as, let's say you have headphones. Or, you know what? This might be a better like explanation. Think about like a TV, right? A TV would be a great example. So with a TV, right, you have multiple inputs. You have HDMI, you have VGA, you have DisplayPort, you even have USB-C. I don't even know how that works, but you have these multiple inputs. Let's say we have an older TV and it only has HDMI and VGA. So HDMI, right, and you have VGA, and these have their respective video outputs, right? And this is going to be the screen. So how do you decide? How does your like TV know like select between the two things, right? You can't just go, okay, I'm gonna and them together, right? Otherwise, you're gonna have a mess. That can't work. You can't or them together either, because again, this can be a mess too. How you can or a video signal. But a great example here is, let's say you have a select switch, right? The select can be either 1 or 0, or you can even have 2-bit selectors, and I can go into that a little bit more. But what would happen is, let's say I have this S, right, and I set it equal to 1, right? What would happen is, as I go through here, this one would be 1, this one would be 0. So, and anything ended with 0 would be 0. And if I add anything by 1, I get itself, right? So, and this will just go through, you have W1. So for S equals 1, I have W1. This looks a bit strange to you because so far I've talked about truth tables with definite, right? If I have select, like if I have, okay, I would assume it looks weird to you. If I have S and I have W1, right? And I have S is equal to 1, we have 1, 0. Then our output here is going to be 1, 0, right? What you notice here is that instead of just writing all the possible outputs for W1, I can just condense this into, okay, well, if S is equal to 1, whatever your W1 is, the function is going to be the same too. So I can just write W1 and that's it. And if I have select is equal to 0, it doesn't matter what W1 is over here. It doesn't matter. For W2, again, if I have, you could go, okay, W2, if I have 1 or 0 or 1 and 0, this doesn't matter at all. This doesn't matter at all. And it's still going to just pick for W1. However, if I have if I select this as 0, then it'll pick anything that is W2, so the function will just follow that. Well, and just be W2. It doesn't matter whatever W1 is, just let's be what the input of W2 is. So instead of writing out all these like 8 possible combinations, I can just write, okay, if I have S equal to 1 or S equal to 0, I have the output of this variable as the output of the function. And that kind of highlights what multiplexer does. If I have select equals 1, I'll have the VGA signal. It'll go to the screen. It'll be a bit crappier, but I mean, I have a VGA cable to my second monitor over here, but then let's say you have W2, it's HDMI. Right, that means you have select is equal to 0, and this one here will instead with a new color. If you have 0, then this one will be 0, this will be 1, and anything ended by 1 will just be itself, and we'll have W2 here, we have 0, 0, W2. right? So that's the basis of a multiplexer. With multiplexes, it involves you can do something. You can continue with more multiplexes, more complicated multiplexes. Um, we have, let's say, select that is 2 digits. So you have S1, S0. It might be, honestly, people should just get a diagram of this off the internet because it's going to take a little while for me to draw it. Okay, here I have a 2-bit multiplexer. So if you notice for, let's say I have both of these are 0, then this one will go on, so go to I0. Whatever, this output would be whatever I0 is here. If I have S0 is equal to 1, then only this one will turn on, so I1 will go through. If I have S1 is equal to 1, then S1, like I have 1, 0 here, then if this one, only 2 is going to go through, and I have both of them on, then only I3 is going to go here. It's actually very, whoever made this, thank you. In that case, though, usually we don't want to use this whole circuit when we want to depict a multiplexer, otherwise it's going to get it's going to be too much boilerplate. So we often use this symbol, right? So let's say you have, we can just actually do the same thing over here. And this is going to be representative of what I have here. Actually, it's not because they're inverted. Stupid. So, yeah. So this is how you can represent what we have over here. So W1, whenever S is 1, we have W1. Whenever S is 0, we have W2. And in this one, I can actually represent it with a bigger multiplexer. So I have, let's say, a multiplexer. We have S0, S1, right? We have I0, I1, 2, I3, and 0, 0, 0, 1, 1, 0, and 1, 1. And that'll be the output over here. Okay. And this is how you can condense this this 2-bit multiplexer into just one output. Now you can go a bit crazy with this. You can go into 3-bit, 4-bit multiplexes. Again, for the sake of time and for the sake of just keeping this as short as possible. I know it's already an hour, but I want to keep. This is how you can have a multiplexer, and this is something that's used all the time in digital circuits. With multiplexes, you can actually use something called, get it, Shannon's expansion. And Shannon's expansion is really great for multiplexes. So let's say you have a function W1, right, W2, and this goes all the way up to Wn, right? This is equivalent to having W1 a complement multiplied or ANDed with F0, W2, all the way to Wn, ORed with W1 just regular, and this is going to be F1, W2, all the way to Wn. Basically, this is basically how you can basically extract, I guess, the first or successive variable. You'd have, so what you do here is, let's say you have f x1, x2, x3, right? You can then expand this into x1 prime, f0, x2, x3, ANDed or it with x1 just regular, f1, x2, x3. And if this original function here is x1, x2, x3, I'm going to try to keep it simple here. x1 complement x2, x3 complement, and then you or it with, let's see, x1, x2 complement x3. So what you do is after the 0 x2, it's where you basically put a 0 wherever x1 is. You notice that only this term would remain. This one would just be ANDed with a 0, so this would become all the 0. This one would be ANDed with a 0, so it would become all 0. So then you have x1 complement, and you have 1 over here. This is x0, x1 complemented, which should be 0 complement, which should be 1, and that would leave you with x2, x3 complement. And then you have x1, and you'd have, okay, so here you have this one. If you had 1 over here and 1 over here and 1 over here, this one would just be x2, x3. This one would become 0. This one would become x2 complement x3. Right, and this kind of breaking down is how you can kind of make something into like a multiplexer. Right, you might be thinking, oh well, come on, this is factoring, right? It is factoring, but in a special way. If we were to take a look at if you wanted to implement a multiplexer with this, oh no, I don't want to do that. I want to implement a multiplexer. Let's say I wanted to have x1 as a selector. Well, if x1 is equal to 0, right, then what you'd have is, oh my goodness, I barely right-clicking pastes. If you have x1 is equal to 0, then the only one that would go on is x2 and x3 complement over here. If you had x1 is equal to 1, then you'd have x3, I'm going to factor on the fly, x2 and ORed with x2 complement, which would actually just be x3 now that I think about it. So that one would just be x3, and that'll be your new function. And that's how you can take any function and just make it into a multiplex. It's really interesting way and a really easy way. And you could take this as many times as you want. You can go further with this, but then you'd have inputs that are just straight up 1 or straight up 0, and at that point, why? you wouldn't need such a multiplex expansion, but you could definitely go further if you'd like. And continuing with that, we have something called a decoder. If you've ever seen, let's say 7-segment display, this is actually a very interesting way of how to do it. Because, okay, with I'll introduce with 7-segment display, and then it will go from there. Yeah. So with a 7-segment display, you have, oh my goodness, you have 7 segments, and usually a dot. And this is called A, D, G, if I'm not mistaken. Or, well, actually, I don't think that works. But the thing is, for a 7-segment display, right? You have 7 outputs, right? You have individual LEDs that need to be turned on, and they need to be turned on correctly, right? It can't just be, this one is on, because what does that mean? It could mean anything. You have 7 outputs, but then you're usually feeding it with a binary representation of the number. You don't want to make a 7-segment display thing go all the way through your circuit. It would be horrible. Nobody would like it, and you'd rather just think about retiring and going off to a distant, deserted island to farm on rather than designing a circuit around 7 segments. But you need to have something to go from a binary number to a 7 segment display, and that's where it is something called a 7 segment decoder. I promise this is relevant. I promise. But what would happen here is you have a circuit element, and you have, oh my goodness, you have, let's say, x0, x1, x2, x3, and you feed it a binary number called x3, x2, x1, x0. And when you have that with a 7 segment decoder, you'd have something, you'd have 7 outputs, 2, 3, 4, 5, 6, 7, and then you'd have an enable pin. And this would just go to your 7 segment display. And eye coordination is at its lowest right now. Here's 7 segment display. And then when you want to, let's say, display the number, let's say you have 1110, then the decoder would know, okay, these ones should not be on, and you should have 7, right? This is a decoder. And a decoder doesn't need to just work for 7 segments. For usual decoder, what you'd have is you'd have, let's say, okay, you'd have, let's say, I'm going to give it 2 inputs. Right, you have W0, W1, and you have enable pin. Enable pin just turns it on and off. That'll be useful in a bit. Then you have, let's say S0, S1, S2, and S3. And you have a truth table that goes like this. You have 4. So let's say you have 0 as your number. Then you have S0 turning on. And all the other inputs are off. And then when you have our number being messed it up because this is not doesn't look like a regular number. Oh my! And let's say you have now instead you have the number 1 going through. Then this 0, 1 would turn off, and then you have all the input is 1, and then you have all the other inputs are off. Same deal with the others. And then you have 1, 1, 0, 0, 0, 1. And this is when enable pin is high, so you have 1, 1, 1, 1. And then when the enable pin is 0, it doesn't matter, then all these are off. So there is a logic circuit to it. I will kind of pause it, and if you want to ruminate on why it works, then I'm just going to move this out of the way. I will make this a bit neater. Perfectionism is kicking in, I swear. And then I will draw the circuit diagram for the decoder here in just a bit. And through the magic of editing, you'll notice that I have a circuit diagram here. Now, what you immediately notice is that you may have thought a bit already, but if you notice 0, 0, so if I have 0, 0, then the only AND gate, I'm going to just assume here that enable is always on. Otherwise, you're going to hear me going, oh, enable, but enable is always on here. And through the only one, let's say I have 0, 0, the only one that would go on is to have all the inputs here. On is this S0 gate. Not this one over here, because this is W0 gate would be off. Then if we had 1, 0, then this one would be 0, and the only gate that would turn on is this S1 over here, because this one is on, and the inverse of this one is on, enable's on, so this one goes through, and none of the others go through. Then for the same deal goes for S2, W1. This one is 1, this one is 0, and this one is on here because now this one is 1. This one here is also going to be 1, enables 1, so only S2 is the only one that goes on. Next, you have W1 and W0 both on, which means, and enables on, which means XS3 here is going to be the only one that's on. And this is the basic principle behind a decoder. For a decoder, you could actually start stringing them up together, and I can actually kind of show. Again, I'm going to take image from the internet here, but there are other ways uh, to implement it. I want to use a simpler one. Yeah. So yeah, here is a 3 to 8 decoder. Oh, paste. Okay, I don't know why paste doesn't work. But yeah, so here, and also some of them are tied to the enable pins. So A0 here goes into, so you have a regular counter up here. So let's say you have, this one goes up to, 3. And then when you start counting above 3, then this A2 will be on, which means that it will disable this decoder over here. So all of these are locked. So all of these, so when this one is on, this one is 0, so then all of these ones are locked. And then you'd have this enable pin turning on, and it would just function like a regular 2 to 4 decoder. And you just have 0, 1, 2, 3, except now you'd label them differently, and you basically deceive the whole world that it's actually that's actually it's and not just a 2 to 4 decoder, it's a 3 to 8 decoder. And I'm going to again steal another image from the internet, and let's just find a simple one over here. Okay, that one's too low quality, but why do they only have 3 to 8 decoders? Because a 4 to 16 decoder will literally just look like you have, yeah, so what would happen is you have, oh man, yeah, I don't want to draw that out. I'm trying to see if there's a thing about it. Because my god, you don't want to see it here. That is interesting. What did they? Okay, here it is. Here is a good one. There we go. Lord help. Thank God. Okay, so here you have we'll call it W. Call this W0. Yeah, basically the basic idea is that you have W0, W1, W2, W3, and you have a number W3, W2, W1, W0. And so basically all these decoders get the same input. So again, these just function like regular 2 to 4 decoders, and depending on what the values between X and Y is, these ones turn on. But then you have this fifth one over here. And so let's say you have the binary number 1100. So this would equal to 12. Now, what would happen is that these ones would both be on, so you'd go through F3. F3 goes to enable this one, and you have 0, 0 over here, and that would lead you to 0, which is equal to 12, right? Let's say then in another example, say you want to have 10, right? 10, so you'd have 1, 0, 1, 0. And you'd have, okay, so this one is going to be second one over here. It's enable. And 0, 1, that'll just be whatever F2 is, and that leads you to whatever 10 is. It's almost like magic because it works. But that's how 4 to 16 decoder would work. And you actually have some, you can actually make a decoder with muxes. Decoders based on mux design, yeah. So 4 to 1 multiplex. Okay, that's very interesting. So you can actually use a decoder. And let's say again, you have W0, W1, have an enable. You have S0, S1, S2, S3. And they have AND gates. And this actually functions like a poor man's multiplexer, except you're not poor because you're using a decoder, but who cares? And then you could just AND everything or everything. You have the output over here. And so you can choose this one. Let's say you have 0, 0, then only this one would go on. 0, 1, only this one. You have 1, 0, then this one, and finally 1, 1, and then this one. And you could just choose whichever one you want, and it's a Richmond's multiplexer. You can also implement this with a tri-state buffer instead. If you really want to use high impedance mode, but it doesn't really matter. It don't matter. It's too easy. And you can even use that to make a ROM block, which is read-only memory. Demultiplexers are the inverse of multiplexers. So you have what you'd have here. That's interesting. So you have demultiplexer. You can tell it's a demultiplexer by the how it's weird inverse of the multiplexer diagram. So then you have, let's see, X, and you have a select pin. Well, you have S0 and you have S1. And what would happen, just gonna copy this, is let's see, you have S1, S0, it's 0, 0, 0, 1, 0, 1. You have Y, 1, 2, 3, 4 again for the sake of time. And you just have X's on the ones that are selected, and then that should not be 1, 2, 3, 4. It should be 0, 1, 2, 3. Then all these things are zeros over here. Right? And then you have a straight diagonal of X's and connect 4. But this is demultiplexer because then you have an input and you have the selecting thing to go to an output. It's actually, I'd say it's really quite similar to a decoder, but not really. It's like a decoder if you smoked some weed and looked at it. It doesn't really. It's not really, but it kind of reminds me. And then you have an encoder where it's the opposite of a decoder. You have, let's say, 4 inputs and you have 2 inputs, and I guess you could have an enable. I don't know why, but then you have y0, y1, y2, y3. You have a condition that you have only one input on, right? And then you have s and s0 over here. So if this is, let's say, 1 0 0 0, then you have 1 0. Sorry, 0 0. it's opposite of a decoder. If you were to feed this into a decoder, then you'd actually have the same here. So if you had, let's say, 0, 0, 1, 0, that would just be binary, not binary representation. This would be the third input, so it'd be, that would be, again, binary is weird. Is there a way how you can say the ordinal of 0? Zeroth? I don't know. But you'd have 0, 1, and then this would just become, again, here. And if instead you had 0, 0, 0, 1, then you have not 0, 1, you have 1, 1, and that would not do that. Go to y3. Yeah, there's actually the circuit diagram. The circuit diagram for it is actually kind of funny because you have W0 here. Sorry, I should say Y0 here, which is not connected to anything. And you have Y1, which is connected to an AND gate, to Y to S0, Y2, you have Y3. So the one Y3, when either Y3 is on, you have S0. That's one. So if you have 0, 0, 0, 1, then both S0 and S1 are on. If you have 0, 0, 1, 0, then only S1 is on. If you have 0, 1, 0, 0, then only this one's on. And if you have 1, 0, 0, 0, then none of these are on. You have 0, 0 encoded, basically. And this would be actually very useful if you have, let's say, like if you have a button, right, or you have like a selector, like a buttons, right? You have 1, 2, 3, or 4, and let's say you want option 1. You click on the first button, and this would be encoded as, as a binary representation of that. Or let's say you want the third option, you press button 3, right, which is Y2 in this case, and that would get you, well, 1, 0. It's a pretty nifty circuit. In fact, I think digital circuits is all nifty. That though, that would conclude digital circuits week 5. Sorry, week 4 here. Because that would be everything. And the next stop is for, oh wow, already midterm content. That's crazy. Sorry, what's somewhat crazy to me is that midterm content is only a month after like the course starts. Holy crap. Okay. This would actually branch into week 5 now that I think about it. Because, yeah. All right. So then this will be week 4 and 5. Otherwise, that wraps up week 4 and 5 for now. And then I will continue on to week 6, which will be sequential circuits. And that will be pretty much that for now.